We are on question 1.2 from this book right here, Generalized Linear Models with Examples in R. And this is very much like question 1, and I probably should have done them together. But anyway, live and learn. So I guess that is to say that if you're just discovering question 1.2 here, you may want to go back to 1.1 as well, because there might be some explanation there that is a little bit useful. But what we are being asked to do is to look at figure 1.8, which I've reproduced right here, and determine which of the systematic components seems most appropriate. Okay. So again, as a reminder, up here in question 1.1, remember that the systematic component, often denoted as either eta, where eta equals x beta, is the systematic component. In other words, the estimate, y hat, represented by the curve, is just eta. It is just our predictor variables times some coefficient that we estimate, okay? So the line represents the systematic component, okay? So which of these lines, i.e. systematic components, seems to best fit the data between a linear model, straight line, a quadratic, which is like a parabola, has an x squared term in there, a cubic, which has an x squared, and an x cubed, and a quartic, which has an x squared, x cubed, and x to the 4th power. Okay, so when we look at these, there's a few things. So of course, the linear model is doing the worst, okay? But now these other three seem pretty similar to me, okay? And so let's scrutinize these a little bit more. Let's start with the most complicated one, and this one is fitting the data best for sure. Almost by definition it is, okay? It has more terms in it, more x terms, so it has an x squared, x cubed, x fourth, that it can kind of manipulate to fit the curve, okay? So it's going to be doing the best, but it doesn't really, to my eye, seem to be doing maybe any better, maybe slightly better than the cubic one here, okay? So it seems like maybe a couple of data points are, it's hard to say. So between these two, the quartic by definition is doing better, but it is probably not doing much better than the cubic, in which case we should prefer the cubic model because it is a simpler model. That is kind of a heuristic at this point, but there are reasons, there are rigorous reasons to take what I've just said that will be alluded to later in the book. And so now let's look at the quadratic one. Again, this one seems to be doing very, very well, but there is a few problems here. So what are the problems? Well, there's really one problem that kind of is expressed throughout the curve here. And that is these systematic departures from the systematic component. Okay, there are these departures that are patterned. Okay, so as we go from like 120 to here or so, maybe what is that? Maybe 125, 1/3, somewhere in there. It is consistently over predicting, and then the line is under predicting pretty systematically. And then it maybe goes, so in other words, the line is consistently under the data points from about here to 150-ish. And then it maybe underpredicts for a while and then kind of catches back into the center of the data. So these patterned deviations from the prediction, that's a problem. And it's a problem because, at least in normal linear models, we are assuming, okay, the model is trying to assume that the errors, that the deviations away from the prediction are random. In other words, they're just as likely to be above as they are to be below the prediction, right? And that's not what's going on here in the quadratic one. So there seems to be some systematic error with this model that is less prevalent and maybe not prevalent in the other two models, okay? So again, to my eye, I'm probably picking the cubic model as being the best one here. Maybe you can make an argument for the quadratic or the quartic. Okay.